Good morning. My name is Sunny Arora, Assistant Professor in CSC Department of Ajay Kumar Garg, College of Engineering, Ghaziabad. Today I am going to take this topic, memory address map. Memory address map is basically the map of the addresses in the memory. For example, if we need a memory size which is larger, but when we have a RAM which is of smaller size, in that case we need multiple RAMs to be applied to make the required memory size. For that, we need this memory address map that will tell you the addresses present in particular RAM, right? So the very first point here says the designer of the computer system must calculate the amount of memory required for the particular application and assign it to the either RAM and ROM. So the designer has to calculate the required amount for the particular application. So the interconnection between the memory and the processor is then established, that is depending upon the size of memory needed and the type of RAM and ROM chips available. Addressing of memory can be established by means of table that specify memory address assigned to each chip, the table called a memory address map. Addressing of memory can be established by means of a table that specify the memory address assigned to each chip. That is our memory address map. That is basically explaining you what is the purpose of our memory address map. Memory address map is pictorial representation assigned address space for each chip in the system. This is a memory address map. It has a few columns. The very first column is our component column. The second one is hexadecimal addressing. Third is address bus. The very first column says the component column specify whether a RAM or ROM chip is used. Whether in the required size of the memory we do need RAM or ROM chip. Okay, it will specify whether a RAM or ROM chip is used. Second is the hexadecimal address column that specify a range of hexadecimal equivalent addresses for each chip. That means each chip will have separate addresses. Third one is the address bus lines. Address bus lines here, this particular memory address map is representing you 10 address bus lines. In general, we have 16 lines, but for this example, we require only 10. In the rest of the 16, the values will be zeros. Now, point number 4, although there are 16 lines in the address bus, the table shows only 10. That I have already explained. The 6 are not used in this example. That is why they are assumed to be 0. Number 5 is depending upon this all X that is in the table. So these small x under the address bus lines designate those lines that must be connected to the address input in each chip. So it must be having some range starting from 0, 0, 0 and so on, all the zeros to all the ones. Now, it is now necessary to distinguish between the 4 RAM chips by assigning each a different address. For this particular example, we choose bus lines 8 and 9 to represent 4 distinct binary combinations. See this table again. We are saying that the bits, the address line 8 and 9, they are basically selecting the particular RAM chip. If we have multiple RAM chips available for the required application. For the we have a big RAM which is made up of these small RAMs. So which particular RAM chip has to be enabled at particular time? So that will be selected by 8 and 9 lines of this address bus. Okay, this is what is this point telling here. The next point, the table clearly shows that the 9 low order bus lines constitute a memory space of RAM equal to 2 power 9, that is 512 bytes. Okay, see this table. Since we are using 9 address line bits, so that means it is making a total memory size of 2 power 9. Okay, I will come again on this part, like 2 power n will represent the 2 power n, where n represents the total number of lines. Okay, the third and the last point, the distinction between a RAM and ROM address is done with address bus line. I have already told you. Here we choose line 10 for this purpose. When line 10 is 0, the CPU selects a RAM, and when this line is equal to 1, it selects a ROM. See this again. The line number 10, okay, the bit number 10 or line number 10, you can say, when it is equal to 1, the ROM will be selected, and when they are like when it is a 0, the line number 10 has 0. When these are all 0, 0, 0, 0, 0, so RAM is selected. Now which RAM is selected? Who will decide that? These lines, number 8 and number 9. If it is 8 and 9 are 0, 0, RAM 1 will be selected, but 10 is 0. When it is 0 and 1, RAM 2 will be selected, the 10 remains 0. 1, 0, the RAM 3 will be selected, the 10 remains 0. When it is 1 and 1, bit number 8 and 9, when it is 1 and 1, it will select RAM number 4, but 10 will remain 0. So in all the cases, we can observe that this is 0. The value in the 10th line is 0. The moment it gets 1, the value of the length, value of the line 10 gets 1, it selects the row. So that was the point number 4 here, which is explaining what is the requirement of 10th bit. Now, equivalent hexadecimal address for each chip is obtained from the information under the address bus assignment. Okay, the equivalent hexadecimal address, see, this is a hexadecimal address. Okay, as we know that every digit in an hexadecimal number will be represented by 4 bits, right? So here the lowest range is 0, 0, 0, 0. So every digit here will be represented by 0, 0. Okay. For example, if I write for 0, 0, 7F, so this will be 1, 1, 1, 1. This will be 0, 1, 1, 1 for 7, and this will be 0, 0, 0, 0, and this will be 0, 0, 0 and 0. So that is making it as a 16 bits, right? So the point is hexadecimal equivalent. So that was the point 1. The equivalent hexadecimal address for each chip is obtained from the information under the address bus assignment. So what do we assign in the address bus lines? That equivalent to that we can get the hexadecimal value, and then that hexadecimal value is lies, basically that is representing the address lies in some RAM. Okay, the second point over here is the first hexadecimal digit represents lines 13 to 16 and is always 0. In this example, in the beginning, I have told you we are not using more than 10 bits because they are all not used, and that is why they are assumed to be 0. So the next hexadecimal digit represents 9 to 12, but lines 11 and 12 are 0. Okay, 11, 12 are also not being used here, so they are 0. The range of hexadecimal address for each component is determined from the X associated with it. Okay, the X represents a binary number that can range from all 0 to all ones. So this is an important point. These X represent a binary number that can range from all 0 to all ones. Now we are going to design a 512 into 8 RAM using the RAMs of size 128 into 8. So we are provided with RAMs which are of size 128, but we are going to make a RAM of the size 512 into 8. So if we have n bit address and m bit words, then RAM size will be 2 into n into m. So that is again important. 2 power n means n bit will give you address lines. Okay, so in this case, as we know, we are supposed to construct 512 into 8. So address lines will be 2 power 512 will be equal to 2 power 9. So address line will be represented by this n, which is 9. So address lines will be of 9 bits. And the basic RAM size we are provided 128 into 8. Required RAM size is 512 into 8. Okay. So before you design 512 into 8, we need to do some calculations. The first formula is number of chips required. Okay. That is a desired RAM size divided by basic RAM size. That will give you what? Number of chips required. Okay. So desired is 512 into 8 and the basic RAM size that is provided to you is 128 into 8. Okay. That will give you number of chips. So that will be equal to how many chips? 4 chips, right? Next is address bits. Address bits is, I have just told you required size is 512 into 8. So that, then you convert this 512 into 2 raised to the power, that is 2 power 9. And this 9 bit will give you address bits, right? And then we have decoder size. Now, why do we need a decoder and what size of decoder will be required? That is depending upon what we'll see here. If the number of words is increasing, then there will be need for a decoder. Okay. When the number of words will be increasing, that means we are given 128 words RAM and you are supposed to make how many? 512 byte RAM. Therefore, the decoder size will be 2 into 4. Okay, because it is 4 times. Okay, so it is 2 power 2, it will make 2 into 4 decoder size, right? So that is how we find out decoder size, because it is 4 times this, and when it is 4 times, you have this 4 here and you can use 2 select lines for that. That means you will be using a 2 into 4 decoder, right? Now, as we know that we will need 9-bit address, and we will divide this into 2 and 7-bit addresses. This 9 bits are divided into 2 and 7. Why this divided into 7 bits? Because the RAM is of 128 into 8. That makes 2 power 7. So, and we have these RAM available size, okay? The basic RAM size that is available to us is 120 into 8, okay? So, we need 7 bits to enable one particular RAM, okay? The 2-bit address will be used as input for 2 into 8 decoder. So, rest of these 2 bits will be used for the decoder select lines, decoder input. The 4 output of the decoder will enable every RAM of 128 into 8. These, suppose we are using 2:4 decoder. What does this 4 means? That means we have 4 RAM available, RAM 1, RAM 2, RAM 3 and RAM 4. So to select one at a time, we need these 2 inputs. For example, if we give 0, 0, it will select RAM 1. We give 0, 1, it will select RAM 2. We give 1, 0, it will select RAM 3. Similarly, if we give 1, 1, it will select RAM 4. So these 2 are for chip select. Which RAM is to be selected? For that, we have this decoder T2 into 4, 2 input for selecting any particular RAM. Which one will be selecting depending upon these 2, okay? The values in these 2. So next is again the same thing I have already explained. Now, how are we going to connect the memory with the CPU? Or right, so we are given here 4 RAMs, RAM 1, RAM 2, RAM 3 and RAM 4, okay? And if you see that memory address map table that I've explained already before, you will see that I have mentioned that there are 16 bits, but 11 to 16 are not required and these are assumed to be 0. That is why these are not shown here, right? And 1 to 7 address bits are for these RAMs, okay? So this is going to, you see this is going to RAM 1, RAM 2, RAM 3 and RAM 4. These are both read and write lines connecting with every RAM chip, okay? But only we see, because we can read and write from the RAM, so therefore these are connected with the RAM. But only read is connected with the ROM, not write line, okay? Because ROM is read-only memory. We can only read data from the ROM. We cannot write the data into ROM. Therefore, write is not connected with this ROM, okay? And we have this CS1 and CS2, which are chip select inputs, and CS2 works on CS2 bar. Basically, it works on 0. That makes it 1, okay? If you give it 0, then it will be working upon 1. Therefore, there is one NOT gate connected to it, right? And this is the input to all the RAMs, okay? Next is which chip at a time will be selected. That will depend upon this decoder. This is a 2:4 decoder here, right? And when it is a 2:4 decoder, which lines are used for these 2 inputs? Line number 8 and 9. In the table I have already explained, if this is a 0, 0, let's suppose this is the bit number 8 and bit number 9. If this is a 0 0, then RAM 1 chip will be enabled. Okay, when these 8th and 9th bit will be 0 1, then RAM 2 will be enabled. When it will be 1 0, RAM 3 will be enabled, and when 8th and 9th will be 1 1, then 4th RAM will be enabled. Okay, but you have to see what value goes on the bit number 10. Okay, like the bit number 10 must be 0 for all the cases when the RAM chip is to be selected. Okay, and 1 for when the ROM is to be selected, right? So that is how we connect our memory chip with the CPU. So that was all in this topic, right? Thank you.